students, in today's lecture we will be discussing about spherical mirrors and how image formation occurs in the case of spherical mirrors and the two different types of spherical mirrors which we have. So, which you must have already had an idea about, convex and concave mirrors. So, that is what we will be learning mostly about image formation and how to understand the image location by using ray diagrams. So, that is what we will be learning in this lecture. Okay. So, basically spherical mirror is made out of a glass sphere. So, if I consider a hollow glass sphere like this, consider that this is a sphere, hollow glass sphere, and if I cut this sphere, let us say with a plane vertically in this manner. So, if I just cut it in this manner, so you can say that there is a small part which is separated out from this side, so which appears to be in the form of a bowl. So, a 3-dimensional structure which is in the form of a bowl. So, that is the part which we will be separating out. So, if I let us say consider this part separately, so which was cut from that, so it would be in the form of a bowl like this. So, with a circular opening. So, I guess you can understand that a bowl with a circular opening, and so this is the one which we will be using as a mirror by polishing different sides of it. So, based on which side we polish, we give a different name to it. So, for example, if I polish the inside one, making sure that the inside one is reflecting by silvering the outer surface. So, if the outer surface is silvered and the inner surface is reflecting. So, if the inner surface is reflecting, inner is reflecting, which is in this particular case. So, then this type of mirror is called as a concave mirror. So, this is a concave mirror. And similarly, if I change the silvering side to the inside such that the outer surface is reflecting, so I will draw it over here. So, in this particular case, if I change the silvering side, so once again the same glass sphere, and now I am silvering it on the inner side. So, when I silver it on the inner side, so this will be the outside surface will be the reflecting side. So, when outside surface is reflecting, outer surface is reflecting. So, in such a case we call that as a convex mirror. So, that is the basic idea here, and generally we can call this concave mirror also as a converging mirror, and convex mirror is generally called as a diverging mirror. Okay. Now, the reason why we call a concave mirror as a converging mirror is because when parallel rays are incident on it, it does not mean that it always converges the light rays. So, the name which we gave for it is based on how parallel rays behave. So, if parallel rays are incident on it in this manner on the concave mirror, so those parallel rays will converge. So, if this is how the incident rays are coming, after reflection from the mirror they converge. So, that is the basic idea based on which we call it as a converging mirror. So, a converging mirror might diverge the light rays also sometimes, which we will discuss in a while, and similarly this is based on the idea that whenever parallel rays are incident on a convex mirror, so those parallel rays will get diverged. So, they reflect from the mirror in the form of a diverging beam. So, that is how the name is given. So, converging mirror and a diverging mirror. So, this is the basic idea. So, to analyze the properties of the mirror and the image formation, we will be first having few terms which we will be using in this particular topic. So, we will first go through those terms. Okay. So, for that, for just explaining it to you, I'll take a concave mirror, but understand that this is same type of naming is applicable for convex mirror also. So, let us consider a concave mirror like this. So we know that this concave mirror would basically be a part of a sphere, which would be something like this. So if this is the center of that sphere, okay, so the naming which we give here would be something like this. So the geometrical center of this mirror is what we call as pole. It is represented with a P, and so I'll write the definitions over here. So pole is basically the geometrical center. Okay. Now after that, so this point here is the center of curvature, we call it as C. So C will represent the center of curvature. Center of curvature basically means the center of the sphere in which that mirror was a part of. So that is basically the center of curvature. Now after that, the line joining the center and the pole, the center of curvature and the pole, is called as principal axis. So principal axis is the line joining C and P. So PA, I will represent it as PA, I will call it as PA. So this is basically the line joining pole, center and pole, C and P. Okay. So that is the idea. And apart from this, we also have one more term which we will be using, a very important term called focus. It is represented with an F, and focus is basically the point here where a parallel beam of incident rays will converge after reflecting from the mirror. So in this particular case, if I consider a parallel beam of light ray like this, so after reflection from the mirror, the point where it converges in this manner. You can also consider one more ray, so another light ray. After reflection from the mirror, the point where the parallel beam of light rays, these are not just for these two light rays, if a parallel beam is incident onto that mirror, so those light rays after reflection will converge at one point on the principal axis, and that is what we call as focus. So this is basically point of convergence of an incident beam or of an parallel incident beam after reflection. Okay, so that is how we define them. Now, there is one more thing which we will be using here, which is basically called as a focal plane. So, focal plane. So, focal plane is basically the plane which is perpendicular to the principal axis and passing through focus. So, what I am drawing here, consider it as a plane. So, like this. So, this is the plane which I am talking about. So, that plane is passing through the focus and it is perpendicular to the principal axis. So, that plane is what we call as the focal plane. Okay, so these are some terms which we will be using in this particular analysis. So, the same way I have considered for a concave mirror, we can also understand for a convex mirror as well. So, the namings will be exactly the same. So, you can write the definition for focal plane, plane passing through focus and perpendicular to principal axis. Okay, so that is the basic idea. So, now let us understand what the location of this focus is. Let us say we know the radius of that mirror. So, if I consider, let us say if I consider this concave mirror to be a part of a sphere which is having a radius of r. So, we all know that this Cp length is what is the radius of curvature. So, let me write that down as well. R is the radius of curvature. of that mirror. So, radius of curvature basically means the radius of the sphere in which the mirror was a part of, is a part of. Okay. There is also one more term which I have missed earlier. So, that is basically called as the aperture. So, I will show it in a different diagram. So, maybe here. So, aperture basically means this opening. So, that opening which is in the form of a circle is what we call as the aperture of the mirror. So, in this particular case, the length which I have represented here, which is the diameter of the circle, is called as diameter of aperture. Diameter of aperture. So, these are the terms: aperture, radius of curvature, pole, focus, center of curvature, and this would be the focal plane, right. Now, let us try to understand where the location of this focus is. How do we locate the focus? Let us say I know the radius of curvature of that mirror and I need to locate the focus, at what distance the focus lies. So, let us try to locate it now. Now, we will discuss about focal length. So, we already have talked about what focus is. So, focus is basically the point of intersection of a parallel incident ray with the principal axis. You can say that the point of intersection with the principal axis can be called as the focus, or if a beam of incident light rays are incident onto the mirror, the point where they converge can also be called as the focus. So, you can understand focus in the two ways. So, one is a point of intersection with the principal axis, that is also the point where a beam of light rays when incident will come and converge. So, if I take one more light ray, so the reflected ray from here and reflected ray from here will converge at that point on principal axis. So, that is what we call as focus. Okay. Now, let us try to find out the location of that focus, and let us say if the focus is somewhere over here, we know that this is the pole of the mirror. So, focal length is basically defined as the distance between focus and pole. So, I will write it down here. This is basically the distance between the pole and focus. So, let us try to calculate that. So, to calculate, so if you look at this diagram over here, so I can say that even though the surface is spherical, we know that loss of reflection can always be applied if I know the normal at that particular position and the angle that the light ray makes with the normal. Loss of reflection can be applied for any kind of surface. So, what I will do is, I will draw the normal here. We all know that for a spherical surface, the normal should always pass through center. So, I will draw a line passing through center and this particular point. So, that will represent the normal, that will represent the normal. Okay. So, now in this particular case, I can say that this angle which you see here is the angle of incidence. So, this is the incident ray, angle of incidence. So, the reflected ray should also make the same angle with the normal when reflecting. So, with the same angle I will draw one more light ray here from that point. So, now this light ray meets the principal axis at this particular position. So, that point is what we call as focus. So, now our idea here is to find out the distance between focus and pole. So, this length. So, that length will be the focal length, and focal length is generally represented with the expression with the symbol f, small f. Okay. So, let us try to calculate that. We know that this is I and this is also I, and if these two angles put together, if it is I plus I, which is 2I, then this angle here should also be equal to 2I, right. And we can even say that if you look at this triangle CF, and let us call this point as A. So, CAF, you can say that this is an exterior angle I. So, this angle here should also be equal to I. The sum of interior angles should be equal to the exterior opposite angle, right. So, I plus I should be equal to 2I. Okay. So, I know all the angles over here. Let me also drop one more perpendicular from here. and I'll call this point as some B. Okay. So now we know the value of AC. AC is nothing but the radius of that spherical mirror. So I'll write it down here in triangle CAF. CAF. So now if you look at the triangle, what I am going to do here is I am going to apply sine rule. So you know sine rule, right? Sine A by A is equal to sine B by B. So I am going to apply that. So now if you see here, this length is R, right? I am going to find out this length. So this one, or maybe we can also find out this length CF. We can find the value of CF. So let me find the value of CF. So I can write CF divided by the opposite angle to this is I. So sin I is equal to, in this case I will use this length now, CA, this length and this angle. So this is equal to R divided by sine of this angle. So sine of 180 minus 2i. What is sine of 180 minus 2i? It is nothing but sine 2i. Sine 2i. So that is the expression which we got. So from here I will get the value of CF. So the value of CF is equal to R sin I divided by sine 2i. Sine 2i can be written as 2 sin I cos I. So sin I gets cancelled and you will be finally getting the expression here as R by 2 secant I. So that is the expression for CF. So I got the value of CF. Now you all know that I need to find the value of PF. So CF plus PF is nothing but CP, which is the radius of curvature. So this should be equal to R. So from this I can directly get the value of focal length. So this value here is the focal length. So F is equal to R minus CF, and the value of CF is R by 2 secant I. So this is the final expression which we get for focal length. Now, but this is not the general expression which you see, because most of the cases which we will be discussing in this particular topic would be a approximated case, and the approximation which we will be using here is what we call as paraxial rays. So understanding paraxial rays is very, very important. So paraxial rays basically means those light rays which are very close to the principal axis and which make a very small angle with the principal axis are what we call as paraxial rays. I will repeat once again. Paraxial rays are those rays which are very close to the principal axis and make a small angle, or you can also say very small angle, with principal axis. So we will be using this assumption throughout this chapter. Even if the question is not, even if in the question it is not mentioned, we will directly assume that we are only dealing with paraxial rays, and you will understand the reason why. So if I consider a paraxial ray, so paraxial ray basically would be something like this. So if this is the principal axis, so the light ray must be very close to the principal axis, so it must be making a very, very small angle with the principal axis. So such light rays which are very close to the principal axis and making very small angles, the light rays can also be like this. We can call this as a paraxial ray, and a light ray which strikes, let us say, over here very close to the principal axis. So this is also making a very small angle with the principal axis. So both the lines which I have drawn there, so both the rays which I have drawn there, both can be considered as paraxial rays. So that is the basic idea. Now what we can say here is that if paraxial rays are considered, then, so now you can see, if I consider paraxial rays, we already have the expression for focus which we have derived as r minus r by 2 secant I. So you see, you can understand basically from here that it is not one single distance. If the value of I changes, the value of f also changes. It means that not all rays, not all parallel rays will come and converge at one particular point. So this is a very, very important thing which you will have to keep in mind about a spherical mirror. A spherical mirror cannot converge. For example, I am talking about a concave mirror, and if parallel beam of light rays are incident onto the concave mirror at different distances from principal axis. So let us say we have 3 rays like this which are parallel to principal axis, but they are at different heights. Different heights will also mean different angles of incidence. The closer it is to the, if let us say this is the center, the closer it is to the principal axis, the smaller will be the angle of incidence, correct? So the closer it is to the principal axis, the smaller it will be to the, smaller will be the angle of incidence. So what happens in this particular case is that all these light rays, because they are incident at different angles of incidence, I value keeps changing, all of them will not come and converge at one point on the principal axis. So you will observe that if this light ray converges somewhere over here, then this light ray will reach here, and this light ray will reach some point over here. So they will reach different points on the principal axis. So that is the reason whenever we use spherical mirrors and we observe large objects basically mean higher angles of incidence also. You will understand that in a while. So what I am trying to say here is that, okay, they converge at different points on the principal axis. So that is what we will observe in this scenario. Now what we are going to do is we are going to take this assumption. The assumption here is that the paraxial rays are only being considered. Now when I consider only paraxial rays, which means rays which are very close to the principal axis, so you know that the closer the rays are to the principal axis, the smaller will be the angle of incidence. We have just seen here, this will be the angle of incidence. So this will be the angle of incidence. So that would be very small, right? So if I consider paraxial rays, we can say that in the case of paraxial rays, the angle of incidence is approximately equal to 0. So it is very, very close to 0. And when the value is very, very close to 0, what is the value of secant 0? Secant 0 will be 1. So which means as the light ray is closer to the principal axis, this approaches 1, and if this approaches 1, this value approaches r by 2, which means the whole value also approaches r by 2. So which means the value of f is equal to r by 2 for paraxial rays. So from this we can say that a parallel beam of light rays which are incident, as long as they are very close to the principal axis and have very small angles of incidence, then we can say that all of them will converge at this particular distance from the pole. So which is what we generally consider as the focal length. So focal length by definition we will be taking it as r by 2, because in all the cases which we will be analyzing with only the paraxial rays. So you do not have to say that this is the focal length. So you can directly say this is the focal length, because as I told you throughout this chapter, we will be considering paraxial rays only, unless and until it is mentioned otherwise in the question, right. We have seen that different parallel rays which are incident on the mirror will converge at different positions on the principal axis, right. So this is basically a defect of that spherical mirror. So a spherical mirror cannot converge all the light rays at one particular position. So you can see here, so a parallel beam which is incident on the on the mirror will not converge at one particular position. That is not just for parallel beam. So it is applicable for light rays coming from any point. So if I consider this is the spherical mirror, a concave mirror, and let us say light rays are coming from over here. So, what we would observe here is that, so if you consider multiple light rays, let us say one light ray is over here, one light ray is striking here, another light ray is striking here. So, to find the position where the reflected rays converge, so what we can say here is that, so another light ray would be the horizontal line, which is the normal incidence scenario. So, if I consider these 4 light rays, let us say, so what is the defect here is that all these 4 light rays, we would expect that if this is the object from where all the incident light rays are originating, after reflection all these should converge at one particular point, but that will not happen in the case of a spherical mirror. So, like I have shown you earlier, so different light rays will converge at different positions. So, this might converge here and this might come and converge here. So, as a result of that, because all the light rays coming from a single object are getting converged at different positions, what you will see here is basically a blurred image. So, this is what we call as a blurred image. So, blurred image, or you can sometimes sense that blurriness sometimes when you immediately wake up from sleep, you see things being blurry. So, that kind of blurriness will basically mean that the image is not being formed at one particular position. So, it is distributed. So, in this particular manner, so that is what we call as blurred image, and this kind of defect that the spherical mirror has is what we call as spherical aberration. So, it is called as spherical aberration. So, you have to understand it that way. If you have to define spherical aberration, it is the defect of a or you can say it is the inability of a spherical mirror to not be able to converge the reflected rays at one particular point, or to not be able to form an image at one particular point. So, that is the basic idea. So, there are some methods which we can use to reduce aberration, to reduce spherical aberration. So, we can use few things. We cannot eliminate it completely, but we can reduce the effect of it. So, one thing we can do here is that, so as you can see, this problem arises if the light rays are striking at different heights. So, first thing is to eliminate that wide range of heights where the light rays can be incident. So, one thing we can do here is by taking a small mirror, by taking a mirror with a small aperture. I am not saying small radius of curvature, please keep that in mind, small aperture. Small aperture means the size of the mirror is very small, it is starting from here and only till here. So, I am only considering a very small bowl kind of thing, not a very big bowl, a small bowl. So, that kind of thing, what kind of help does it do? So, when I am taking a small mirror, only the paraxial rays are going to strike the mirror, which means light rays which are making small angles with the principal axis, only those are going to strike, and when only paraxial rays are striking, we know that all light rays will converge at focus, which is r/2 distance from the pole. So, that is one thing which we can do. The second thing we can do here is basically block all the marginal rays. Marginal rays basically mean the light rays which are striking at larger angles or at larger distances from principal axis. So, you can see that these are light rays which are striking at far away distances from the principal axis, as a result of which the angles of incidence are also larger. So, this is the angle of incidence. So, it is a large value. So, to eliminate those rays, and so these are basically called as marginal rays. So, how do I eliminate or how do I block the marginal rays? The idea is pretty simple. What I will do here is, I will just take a cardboard, any opaque substance, I will take a cardboard and I will make a hole in it in this manner, in such that the axis of that hole coincides with the principal axis. Now, what happens due to that? So, what happens in this case is that all the marginal rays would be blocked and only those light rays which can pass through the hole will pass through and strike the spherical mirror. So, that is what happens here, and those which can pass through the hole will be making very small angles with the principal axis. So, they can be considered as paraxial rays, and for paraxial rays spherical aberration will not be significant, it will not be observed. All the paraxial rays go and strike the mirror and converge at a single position. So, that way we can reduce the effect of spherical aberration. I am not saying we can eliminate it, but we can reduce the effect. The blurriness in the image will definitely decrease. So, that is the basic idea. So, to block all the marginal rays, right. So, now let us start analyzing the image formation in the case of a spherical mirror. So, to be able to do so, we need to know some standard ray diagrams which we will be drawing to locate the image. So, first we will talk about some standard ray diagrams. So, first one which we can say here is that if I consider a light ray which is incident onto the spherical mirror in such a way that it passes through the center. So, which means the light ray which is incident on the mirror is incident in such a way that it passes through the center. So, this is the case. So, if there is a light ray which is incident in this manner, how would it get reflected? It would get reflected in the same direction backwards. And what is the reason for that? Because the line passing through center will also be the normal. So, this will also be the normal. So, it is basically normal incidence. So, it is just striking the mirror perpendicularly. So, at this surface it is striking perpendicularly. So, a light ray which is incident in such a way that it passes through the center of curvature will get reflected in the same direction backwards. So, that is what this light ray basically means. Now, similarly, next thing we can say here is that if a light ray is incident in such a way that it is parallel to the principal axis, you all know what happens in this scenario. So, this point let us call it as focus. So, the light ray will get reflected in such a way that it passes through the focus. So, as I told you earlier, I will not be telling you each and every time that these are all paraxial rays. By default, we will be considering only paraxial rays throughout the further analysis. I will not be telling it each and every time. So, but understand, so do not think that these distances are very large, these angles are very large, so how can they be paraxial rays? So, that is just a way of representing for you to understand. So, whatever we are doing now is only for paraxial rays. So, keep that in mind. So, do not look at these distances, that is for your viewing. Okay. So, a light ray parallel to principal axis will get reflected in such a way that it passes through the focus. Now, similarly, so here this is the focus. So, next we can say that if a light ray is incident in such a way that it passes through the focus. So, if this is the incident ray, now what will happen to the light ray after it gets reflected from the mirror? It becomes parallel to principal axis. It is just the reverse of that basically. Next, let us consider that there is a light ray which is incident at the pole at some angle I. So, in this particular case at pole we can say that principal axis will also be the normal. So, because this is also the normal, I can say that the reflected ray will also get reflected such that it makes the same angle I with the principal axis. So, these are some standard ray diagrams which we will be using. So, what I have shown you here are for a concave mirror. So, a similar such analysis can also be done with a convex mirror, and in convex mirror you should be little bit more careful, and the reason for that is what you will see now. In the case of a convex mirror, we can say that the focus and center will be behind the mirror. So, they will be on the other side of the mirror. So, that is the reason why we call them as virtual focus. So, these are all called as virtual focus, because even if a parallel beam of incident ray is taken, for example, let us say I have taken a parallel beam of incident ray onto the convex mirror, you know that after reflection, because this would be the normal. So, this is how the normal would be. So, after reflection it has to follow laws of reflection and it should get reflected like this. Now, in the same manner, if another light ray is taken like this, so this will get reflected in this manner. So what this means is that this is one reflected ray and this is the other reflected ray. So these two light rays are going like this. So they are not actually converging at the focus, but they appear to converge at the focus. The point of intersection of these two reflected rays is appearing to come from focus. Unlike the earlier scenario where they actually converge at the focus, in this particular case you will observe that these light rays, they just appear to come from the focus. So in this manner. So that is the basic idea. So that is the reason why we call it as the virtual focus. Anyways, now just like the earlier case, if I draw ray diagrams even in this case, so if a light ray is incident in this manner in such a way that it appears to pass through center. So what the light ray I have drawn there is incident on the convex mirror in such a way that that is appearing to pass through the center, because it can't actually pass through the center because it is on the other side. No light ray can travel to the other side. So if the incident light ray is incident in such a way that it appears to pass through the center, then the reflected ray will get reflected back in the same direction, because at this point this will also be the normal, the same logic which we have applied earlier. And this we have just seen. So if I consider a parallel beam of light ray, so this parallel beam of light ray, if incident, it gets reflected in such a way that it appears to come from focus. It does not actually come from focus, but it appears to come from focus. Then similarly, if I consider a light ray which is incident like this, such that it appears to be passing through the focus. So the incident ray appears to pass through the focus. In this case, we can say that the reflected ray becomes parallel to the principal axis. So please look at the directions of these light rays carefully, that is very important. So this is the incident ray, it is appearing to go towards the focus, but after reflection it just becomes parallel to the principal axis. And this is the same thing which we discussed earlier. So if I consider a light ray which is incident at the pole at some angle, because principal axis is the normal, it gets reflected at the same angle. So these are some standard ray diagrams which we will be using in the case of concave mirror and convex mirror in the next coming cases to locate where the images are being formed, right. So please make note of it and also write down what each case represents. Incident light ray passing through center, reflected light ray will retrace the path backwards. Incident light ray parallel to the principal axis, reflected light ray will pass through the focus. So in that way, please write down each and every meaning for each individual case, right. Now let us see how image formation is happening through ray diagrams. Now we will understand the image formation in the case of a concave mirror. So I will be drawing ray diagrams, I will be taking the object at different positions, and I will see where the image is formed, how the image is formed, what size will the image have, and cases like that. Because I am also going to understand the size, I will have to take an extended object. So I will take an extended object. So let me first consider that the extended object is initially placed between the focus and pole. So we will be discussing 4 cases. So in the first case, the object is between pole and focus. So let me write it as u. U represents the object distance from pole. So u means object distance from pole. Okay. So let us find out So in the first case, I am considering that the object distance lies between 0 and f. So which means the object is between the focus and the pole, right. So let us see. So if the object is like this, let's consider it as an extended object in this manner. So you know that when there is an extended object, I can take the extended object as 2 point objects at the 2 ends and locate their respective images and join them. In this case I do not even have to take 2, I will just take one which is the topmost point. I will find where the image of the topmost point is formed, and then I will just drop a perpendicular onto the principal axis, and that point where it touches the principal axis will be the image of the lower point. So, you will see that. Okay. So, I am placing the object between the focus and pole. So, now we have 4 standard ray diagrams which we have considered earlier. You can draw any 2 of them. To locate the image, we know that we need at least 2 ray diagrams. So, I will draw any 2. So, first what I will do is I will consider a light ray which is incident parallelly, and if the light ray is incident parallelly, we know that after reflection it should pass through focus. So, this is how the light ray would be after reflection. So, it gets reflected in this manner. Okay. Now, let us take one more light ray. This time you can consider that the light ray is passing through pole, right. Another light ray I will take to be passing through pole. So, this will be the angle of incidence. So, I will draw one more light ray which is incident at the same angle, which is reflected at the same angle. So, this is how the reflected ray would be. So, I got 2 reflected rays in this case, this is one and this is one. So, you can see that in this particular scenario they appear to be diverging from each other. So, which means the point of intersection of those two will be actually behind the principal axis, behind the mirror. So, they two might converge behind the mirror. So, when I extend them backwards in this manner, so I will observe that they converge at some point over here. So, this is where the image would be formed. So, if I consider this as A, so the image of A will be formed over here, and you can see the image which is formed is definitely a virtual image, because the light rays are not actually coming from there. This mirror is making us believe that the light rays are coming from there, whereas it is just getting reflected from the mirror. They are appearing to come from a point which is behind the mirror. There is nothing behind the mirror. So, in this particular case we can say that image which is formed is basically a virtual image, and by looking at the diagram you can easily understand that the size is bigger. So, which means it is a magnified image, magnified, and you can say that it also is having the same orientation as the object which we have taken. So, it is also an erect image. So, these are the points which I can say about this scenario where 0 less than u less than f, object lying between focus. So, this is the focus and pole. So, that is the idea. Okay. Now, let us talk about the next scenario. So, in the next case what I will do is I will move the object little bit backwards, I will bring it between the center and the focus. So, let us place the object here. So, that is where the object is, and let us draw the light rays once again. So, I will write down this case here. So, this case corresponds to f less than u less than 2f. So, object lies between this and this. Okay. Once again this time I will consider a light ray which is passing through focus. Just to change, earlier we have taken light ray parallel to principal axis, this time I am taking a light ray which is parallel to, which is passing through focus. We all know that after reflection this light ray should become parallel. So, I will just draw a parallel light ray. So, after reflection it just becomes parallel to principal axis. So, this is one light ray that would get reflected, and if I consider one more light ray, you can consider any other light ray. If you want, you can take the one which is passing through the pole, or we have done that already. So, let us take one more light ray. Let us consider a light ray passing through center. So, if a light ray is incident in such a way that it appears to come from center, or maybe I should draw it little bit higher. Okay. So, if there is a light ray which appears to come from the center, so a light ray which is incident in this manner. So, you know what happens to that light ray now? So, this is the incident light ray. From here it moves like this, and because it is coming from the center, appears to come from the center, after reflection, it just retraces the path and it just goes back, it just moves in this path and it intersects this another reflected ray at this point. So, if this point here is A and this is B, so we can say that if I extend this, so this is where the image of A will be formed, A dash, and if I drop a perpendicular, so you will observe that this is how the image is formed. So, you can observe that, right. So, now just like we have written the nature of the image formed in this scenario, let us also write the nature of image formed in this case. So, can you guess what it might be? Obviously, it looks inverted, it looks larger than the object. So, that we can say. What about its nature? What about whether it is a virtual image or a real image? Is this image being formed due to actual intersection of reflected rays, or it appears so? You can easily see that these are actual rays which are meeting here, which are actually intersecting here. So, we can say that this is a real inverted and magnified image. So, that is what happens in this particular scenario. So, that is the idea. Okay. Now, let us move on to the next case. So, this time let us consider that the object is placed after the center. So, between the center and infinity, right. So, let me write it down over here. U is greater than 2f, which means it lies after the center. So, let me take that object over here. So, let us consider that this is the object. So, I am placing it after the center. So, same, I will take two light rays and trace them. One light ray I will take parallel to the principal axis, it passes through the focus. Another light ray we can consider, you can take any light ray, you can take one light ray passing through focus, it reflects here and it turns back parallel to the principal axis and it meets the other reflected ray at this position. So, the image will be formed in this manner. So, this is what happens, right. So, once again you can understand the nature of the image formed. So, this is the object, this is the image. So, if you look at the image, you can say that it is once again a real image because two actual rays are intersecting at this particular point, right. It is a real image, it is inverted, and what can we say about the size? It is smaller. You do not have to rely on whether it looks smaller or it looks bigger. We will actually have a formula which we will be deriving for it. So, for now it looks smaller. So, I can just say that it is diminished. So, that is the idea in this case. Okay. Now, the last case, so is actually a virtual case. So, this is a case where the object is virtual. Object is virtual. So, you may get a doubt, can there be virtual objects? Can an object lie behind the mirror? So, what that means is whenever you see this term object is virtual, you should understand that the light rays which are being incident onto the mirror, the light rays which are incident on the mirror, they are not actually coming from a point and moving like this, they are not diverging light rays. If the light rays incident are diverging, they are coming from an actual point which is in front of the mirror, right. So, that is what we have seen in all these cases. So, in this case also the incident rays are diverging, incident rays are diverging. So, even here the incident rays are diverging. So, whenever we have a real object, the incident rays will be diverging. Now, when do we have a virtual object? When the incident rays are converging. So, as simple as that. So, let us consider a virtual object like this. So, I will be drawing the incident light rays such that I am trying to locate the image of this particular position, just like we have done in all the earlier cases. So, I have taken this as the point object and tried to locate the image. So, in the same manner I am going to take this topmost point as the object, but the only thing is that the light rays do not actually intersect there, the incident light rays, they appear to intersect there. So, I will take two light rays that way, I will take one parallel light ray which appears to reach the topmost point, and I will take one more light ray passing through focus which appears to meet at that particular point. So, I have taken two incident light rays here. So, once again remember, these are incident rays, these are converging, they converge behind the mirror where there is no object actually. So, that is why we call this as virtual object. So, these light rays are appearing to come from here. So, that is the idea. So, let us trace these light rays backwards. So, when I trace these light rays, so we know that this parallel light ray should pass through the focus. So, let me draw it again. So, it should pass through the focus in this manner. So, this would be the reflected ray, and the other reflected ray which is striking here, because it is passing through the focus and striking, it should become parallel to the principal axis. So, the next light ray will be like this. So, now see where is the intersection point of the reflected rays. Once again observe carefully, this is one reflected ray and this is the other reflected ray. So, where are these two reflected rays intersecting with each other? At this position. So, this is where the image is formed. So, that is how you can understand, and you can tell the nature of the image formed in this case. So, this is formed because of actual intersection of two light rays. So, it is a real image, it is erect and it is diminished in size. So, that is the basic idea. So, that way we can understand the location of the image formed and the nature of the image formed just by using ray diagrams. We will also understand all of this by using the mathematical derivations as well, which we will do in a while. We will also understand it graphically by plotting the graph between object distance and image distance. So, we will see that analysis. So, what I want you to do is, I want you to do a similar kind of analysis for a convex mirror, right. So, convex mirror would be a case which would be like this. So, even in that case you can try 4 different scenarios. So, you will have focus over here, you will have center over here. So, what I want you to try is the 4 similar cases for a convex mirror. I will show you what those 4 cases are. One is a real object placed in front of the mirror. It can be placed anywhere. There is no segregation on this side, there is segregation only on this side. So, we have 3 different scenarios on the other side, but not on this side. I hope you are understanding. In the case of concave mirror, there are 3 possible real cases which we have seen, and there is only one possible virtual case. Everything behind the mirror is the same. In this case, everything in front of the mirror is the same. So, wherever you place the object in front of the mirror, the nature of the image formed will be the same. So, you will understand that if you draw the ray diagram for this scenario. So, next case would be a virtual object between focus and pole, a virtual object between focus and center, a virtual object between center and infinity. So, 4 different cases. So, these are virtual objects, this is a real object. So, try to draw the ray diagram. So, I will discuss 1 or 2 of these cases in the next class. Okay. So, that is the basic idea. So, we will now see the derivation of mirror formula.